So I'm Mohammed. I'm a senior lecturer in mechanical engineering, and I'm going to give a brief introduction on the engineering at nanoscale around my research, what I do at the University of York. And I need to also mention that because I'm looking to another screen, excuse me if I look away from the camera. So I'm going to start my I'm going to start my presentation by just briefly talking about the history of nanotechnology. Excuse me, some difficulty I have with the two screens. Then I'm going to talk about why nanomaterials and nanostructures are quite special and what are the unique features they're offering in engineering design, and then some of ongoing research at the University of York, especially focusing on my research into two pillars of research I'm doing in the area. And then we'll look around what's going to happen with nano devices in future technologies. So by starting the history of downscale device and what happened and first it started when and how it's evolved. First thing first, most of the people think that nanotechnology is around for a couple of decades, but we know and we have evidence that nano device and nanotechnologies happened hundreds of years ago. For example, in light microscope made in 200 AD in the ancient Roman and medieval artists randomly utilized nanoscale effects by mixing gold and silver nanoparticles to change the color of glasses and cups. For example, in this case, you can have different colors for the cup, and the cup could be transparent based on the properties of the incident light and also the angle of the incident light. So you can get a very different optical properties, or let's say on that time they called it optical illusion. So it's been around here, but we know that there was no technology or science behind it. The main science and technology started in the Industrial Revolution around 18th and 19th century, and scientists and engineers, they were quite curious on the complex systems. During the Industrial Revolution, inventions like steam engine and telegraph, they revolutionized and they changed the modern industry, transportation, and communication. So engineers, they were always looking into a complex machine, and they were trying to build a machine that could address all the human requirements and needs. So they were always looking to build a complex and multifunctional machines. But not only they were looking into complex machines, but also they were looking into a smaller scale and try to find out what is the fundamental building block of materials. That led to understanding of atoms, electrons, molecules, and the first basics of every material. So beside every complexity, scientists were also looking down there. So around 1974, the phrase nanotechnology first used, and it was referring to the precise manipulation of atoms and molecules. But that was mainly popularized by the famous talk by a physicist, which is one of the high prestigious and famous physicists in the community, was Richard Feynman, who said there are plenty of rooms at the bottom. And that envisioned building machines and structures atom by atom. That was a kind of a brief history around when the nanotechnology started, how they started to think about nanotechnology. But it was around mid-20th century that humans start to build first computers. However, the first computer was quite impressive, but comparing to nowadays, it was pretty primitive. And volume, with respect to the volume, they were quite chunky and bulky. Some of them, they were in the size of a room, made of less than 100 transistors. But over the time, technology pushed those computers to become smaller and smaller and become more and more powerful. And nowadays, we are carrying millions and billions of transistors in our pocket as a smartphone, or we can carry them in our handbag, in a laptop or tablet. So you can see that this downscaling is helping for complex machines. Downscaling was not the only answer to reduce the size or make it lightweighted or make it more powerful. But also, it was trying to go with the direction that Industrial Revolution made of curiosity to complexity. because we tried to build one single machine which could address all the requirements and could be helpful for our daily life. Mobile phone is a very best example. The first generation, it was started around 40 years ago. Mobile phones, very heavy, very chunky. They were just used for the phone call. Then a few years after that, short message added, gaming added. Then after that, vibration features, colorful LCDs or screens. Early 2000s, camera added to mobile phones. Mobile phones were able to play music, or they became radio. They added to the Bluetooth features, and also memory stick, so we can have hard drive in our pocket. Couple of years after that, mobile phones get connected to the World Wide Web through wireless communication. Then we had touch screen, different applications, wireless charging, voice recognition, fingerprint, QR code, high-tech camera. And these days we use our phone as our wallet, or we can use it as a scanner. As you can see here, we not only have downscaling device, but also we have multifunctional device. So we are building machines that are complicated and they're a smaller scale, and that is thanks to the engineering at nanoscale. Why this happened? So many devices start to become smaller and to be more powerful. One of the big examples is transistor. Transistor helped to make such a revolution in industry. First generation of transistors, they were vacuum tubes. They were quite bulky, again, a few centimeters. You couldn't integrate more than a couple of them because of the technical issue, but semiconductor manufacturing formed, and they were able to reduce the size of the transistor into a few millimeters, then after a couple of years into a few micrometers, and nowadays it's in a few nanometers. And that helped us to have mobile phones from bulky ones for single function of phone call to a very lightweighted multifunction device. So transistor was not only the single device that could help us to move on towards that direction, but also we had so many other electronic, mechanical, thermal, chemical sensors and devices that they move to the right, to that direction of downscaling. For example, mechanical sensors, thermal sensors, optical sensors, filters, signal generators, and many other devices that helps us. Nowadays, we can have smart robots. So robots could do so many jobs in industry, and that's thanks to transistors and many downscale devices. We can have high resolution sensors for automation, so we don't need drivers in the vehicle, so we can have a precise navigation in the vehicle, moving toward autonomous vehicles. We can digitize bioinformation, so we can move towards the digital healthcare. And new era for virtual reality, of course, is an interesting area in industry. So I've been talking about nanoscale and nano device and nanostructures. One might say, what is nanoscale? Let's take a look and see and get some sense about the nanoscale. A human hair, which is barely visible with the naked eye, has a thickness around 100 micrometer. An average device of a nanostructure, which we carry in our pocket, in our mobile phone or laptop, has an average size around 100 nanometer. So you can see that a nano device is around 1,000 times smaller than a human hair. To get a better sense, let's compare London Eye with a tennis ball. London Eye represents human hair. Tennis ball represents a nano device. Now you can imagine how small we are talking about. We are talking about a very, very small scale devices. Now, having those nanoscale devices, we can take a look and see why they are special, what makes them quite special, and what features and properties they're offering us. There are two key features. Actually, there are more than two key features, but for the time being, let's stick with these two ones. Which is high surface to volume ratio and quantum confinement. These are two major features in nanomaterials that make them quite unique. So what is the surface area to volume ratio? Let's take a look at a very simple math question. We have a cube of 8 by 8 by 8. We reduce its size to the size of a cube, which is 2 by 2 by 2. If you do a bit of a simple math, you can find out that the surface area to volume ratio by this downscaling or reducing the size increases 4 times. Now imagine that if you reduce the size of a device from a few micrometer to a few nanometer, you increase the surface area to volume ratio significantly higher. So you have high amount of surface compared to the bulk. Now, what happens when we increase the surface area? Again, let's take a look into down into the physics of materials. Materials are made by atoms. Atoms in materials are sitting in a well-organized fashion. Actually, most of the materials are atoms are sitting in a well-organized fashion. They bind together in a very good energy balance. So one atom in the bulk of the material has all its neighbor connected to all of them. They keep each other, they hold each other, and they're in a balance in the energy. But what happens in the atoms on the surface? Unfortunately, they lose neighbors. They have lack of neighbors, so they don't fully occupied by the neighbors. So this lack of neighbors, therefore, we have a different bonding profile compared to the bulk. So we have different balance and energy level in the atoms on the surface. Now, by increasing the amount of surface means that we increase these atoms which are losing their neighbors and they're in a different energy level. That means that the properties of the materials start to change. So by changing the proportion of the surface area to volume ratio, which change this surface energy, therefore we change the properties of materials. That's one of the reasons that makes materials at the nanoscale very unique. The second reason is quantum confinement. In a very simple phrase or very simple statement, electrons in bulk materials in a micro scale or macro scale, they can fly freely in a different level. So they can fly freely in the bulk material. So their energy density is kind of continuum. So they can fly without any restriction. But as soon as we reduce the size of materials, they become confined in the nanoscale. So they can't fly freely, and they are limited to fly in a specific energy. Therefore, their energy becomes discretized. Therefore, we have a different properties at nanoscale compared to the bulk macro scale structures. So what happens by increasing the surface energy and quantum confinement? Some of the benefits of this downscaling. We can have electrical conductivity in non-conductive materials. Some of the brittle materials becomes flexible. We can have anomaly properties, a giant heat transfer, a giant and significant increase in the strength, mechanical strength, electrical conductivity, or obviously, when you reduce the size of the device, you can have more device in a smaller volume, and many other benefits that nanoscale structures could bring to engineering application. Let's now take a look at some of those properties at nanoscale. In the electrical properties, we can have better data storage and data processing. Spintronic in nanoscale can give us a very unique property, so we can leverage those electron spin in nanoscale and can have more powerful data processing and data storage. And that's the reason we can have a very small memory stick in the size of a fingertip. It could be a gigabyte or terabyte memory stick. However, in the old days, we could just have a few bytes or megabytes in a big chunky hard drives. But nowadays, the hard drives are getting smaller and smaller, and they become more and more powerful. High-speed transistors are also another benefits we can get from a unique properties of the transistors. For example, when we reduce the size of the transistors, they become faster because in a very simple phrase, transistors are devices that we control electricity by electricity. So they're like a gate. They become on and off. How quickly we can turn them on and off, it depends to the size of the transistor. When we make them smaller, they become ultra-fast electronic components. So they become fast logic gates. So we can turn them on and off much faster. And that helps us to have new generation of radio frequency, 5G and 6G wireless communication systems. Magnetoresistive is another properties As an example, we can get from nanomaterials. We can get giant magnetoresistance for precise magnetic detection. Gyroscope is a key component in navigation. And when we have a high precise gyroscope, we can detect the navigation of the system. For example, in a vehicle, we can find the location easily, the change of the location easily we can control. And therefore, by having a giant magnet resistance in nanomaterials, we can have new generation of sensors suitable for autonomous vehicles. And that's an ongoing, interesting area for autonomous vehicles. A few examples on the mechanical properties. We can have flexible electronics. So we can, as I said, some of the brittle materials become flexible. So we can have foldable conductive materials, which are suitable for foldable and bendable display and sensor. They could be variable sensors. We can add nanoparticles to the glass, and we can make them anti-scratch or scratch resistance, which are very unique and special for optical lenses and displays, so they can have longer lifetime by adding nanoparticles into the glass. Or if we add, for example, nanofibers into the nanocomposites, we can have lightweight, higher strength structures, which is very suitable for aerospace application and aerospace industry. Because in aerospace industry, we are always looking for strong structures which are very lightweighted, and nanocomposites are offering such an opportunity. Another properties which would be thermal properties, and these days we are using more and more electronic systems and power electronic systems. Nanomaterials such like carbon nanotubes and nanoparticles, graphene, they are offering extreme high thermal conductivity to take out heat from power electronic devices. These days, electric vehicles are getting more and more popular, but one of the key challenge is to take the heat generated in the battery and power electronic devices out of the system. Otherwise, the system could go into danger and there's a risk of explosion in the battery. So thermal management is quite critical in energy system of the electric vehicle. So nanomaterials such like carbon nanotube give us such an opportunity by proposing extreme high thermal conductivity. So we would be able to come up with advanced thermal management system and take out any heat generation, any heat generated in the system, and take it out from the battery. Or from the other side of the end, nanomaterials such like porous silicon could give us opportunity to have extreme low thermal conductivity to insulate a spacecraft or satellite. We know that out in the space, the temperature is extremely low, and this extreme low temperature could be detrimental to the astronauts in the spacecraft or all the mechanical and electronic facilities inside the satellite. So we need to protect it from those extreme low temperature out there in the space. So we need to insulate it, and we need to keep the heat inside the spacecraft or satellite. Porous materials such like silicon give us such an opportunity to come up with extreme low thermal conductivity, and they're very suitable for thermal insulation. They were just a couple of examples. I talk about the nanomaterials, how they could offer us unique electrical, mechanical, or thermal properties. There are obviously other unique properties like magnetic properties, optical properties, but it was just a couple of those examples. How do we fabricate or how do we manufacture those nanostructures? Obviously, we need to have a unique environment, because if we have particles and if we have human hair around the nano device, then you can imagine that you organize all these tennis balls and London Eye would fall on top of those ones, so you can easily break them. So you need to have a very clean environment. So the special equipment is called clean room. So in these clean rooms, you need to have a proper protection of using those facilities to protect the fabricated device from any particles on any dirt that could damage the device. There are various machines that are used for fabricating those nanoscale devices, such like electron beam lithography, etching, thin film coating, that you can create those nanoscale devices for different purpose. But when you fabricate or manufacture them, you need to obviously test them and make sure that you have good integrity and you can achieve the properties that you were planning. Atomic force microscopy, electron microscopy, and many other microscopic devices, they are helpful for that purpose, because obviously we won't be able to see those nanoscale devices with normal optical microscopes because the size are pretty small and you need to have unique facilities for that. Obviously, when we have opportunity, new challenge and new technologies, challenge would be following those technologies, and we have different challenges to develop nanoscale devices. The first challenge is, at the moment, we have limited understanding on the properties. Some of the nanomaterials are well understood. We can easily predict their behavior when we reduce their size. For example, gold, when we reduce the size of the gold, the mechanical strength goes up, so we can easily design a gold nanostructure as a mechanical device or electronic device because the behavior when we reduce the size is predictable. But unfortunately, there are some key elements or key materials, such like silicon, that still we don't have a clear understanding what happens when we reduce the size of the material. For example, in silicon, when we reduce the size of the structure, some results show that the properties of mechanical properties goes down. Some results shows increase. Some results shows that there is no change in the properties. So still we have limited understanding on some key elements. When we reduce the size, what happens? So we need to know the size dependency and the physical behavior when we reduce the size of the material. Complexity in fabrication and testing of nanoscale device is another challenge. However, those devices are pretty small and very small scale, but the machines to fabricate them or test them are quite huge and big machineries. And we need to have high resolution sensors to create a high resolution sensor. So now you can imagine how difficult it is to calibrate and develop a new technology to develop the same approach. So complexity of fabrication and testing at nanoscale is another challenge. The last but not the least is complexity in materials modeling and nanoscale. Understanding the physics, what happens when we reduce the size. Because when we are engineering design, we need to have a proper design approach. There are loads of design approaches for nanoscale structures, from first principle, molecular dynamic simulations, multi-scale simulations, and finite element methods, and so on and so forth. But unfortunately, those mathematical modelings are made based on some assumptions, and that led to some gap between those modeling approach and experimental measurements. So still there's a gap between experimental measurements and computational modeling, and bridging this gap would be very helpful for having a proper engineering design of a nanoscale device. So what I do at York, or some of the ongoing research at University of York, I want to talk about it briefly. It has two pillars. The first pillar is about better understanding of the properties. Understanding the properties of silicon, because silicon is abundant on Earth, is key building block in semiconductor manufacturing. And pretty much over the past couple of decades, semiconductor manufacturing was established around silicon because it has very unique features. But unfortunately, as I said, there are still some areas and angles that we don't understand the behavior of silicon at nanoscale. So I'm doing the research in that area, and I'm trying to understand what happens with silicon. And recently, for that vision, we developed a new monolithic technology to integrate nanoscale device with the microscale systems. That means that we were able to isolate a nanoscale bridge or nanoscale wire between two micropillars. If I want to give you a size of these dimensions of these structures, the nanowire is around 50 to 100 nanometer, and the micropillar is around 50 micrometers. So it's about 3 orders of magnitude scale difference to integrate monolithically nanoscale and a microscale at the same time. And we were able to establish this technology on silicon, which is a key element component in semiconductor manufacturing. So one might say that, so what would be benefits? So now we have this integrated nanoscale and microscale. What can we do with it? Okay, first thing first, we isolate nanoscale from its environment. The second is that working and manipulating nanoscale is very challenging and difficult, but manipulating and working in a microscale is much, much easier. Now, when I have the integrated system, rather than controlling and working in a nano device, I can manipulate and work the micro device, but getting the benefit of the unique features and properties of the nano device. Fortunately, we were able to implement that device into the different application. For example, integrated the microsystem and nano device for new generation accelerometers, which are based on the piezoresistive readout. We were able to create a new generation of resonators and band pass filters that they could be used for next generation of radio frequency applications. And also, we applied this technology to create a new in-situ characterization approach because we were able to take out this isolated nanoscale into the different microscopic system. And because the nanoscale is isolated from its environment, it's easy to access. And therefore, we were able to characterize it by Raman spectrometry, optical sensors, mechanical characterizations, and we were able to not only mechanically characterize the system, but also we were able to measure the surface properties, which is a key aspect, as I said, by increasing the surface area to volume ratio, understanding the surface atoms and what happens when they lose their neighbors, how they change the properties of materials. We were able to characterize them, and using different computational modeling, and try to bridge the gap between computational modeling and having a better understanding on the mechanical properties of silicon at the nanoscale. Our recent finding shows that, interestingly, silicon nanowire creates a native oxide, which is a silicon dioxide, and it's amorphous, and it can form and it can bring different surface properties to the silicon nanostructure. That means that the native oxide can reduce or increase the mechanical properties. So that is one of the area that we're still exploring, because this native oxide can form and can create different surface properties for silicon and nanostructures. And that's one of the area to address the complexity among the literature. And that's one area that is trying to answer why silicon sometimes showing the low reduction in the mechanical properties and sometimes showing the increase. And that is what we are coming to the conclusion, that native oxide formation is the key element in here. As I said, nanostructures, they have complicated physics, surface area to volume ratio, high surface energy, quantum confinement. How they are changing the properties of nanomaterial would be sometimes very complicated, and classical computational modeling and mathematical modeling sometimes could not answer those questions. But thanks to artificial intelligence and progression in machine learning, we were able to implement machine learning and AI to first predict the surface behavior and find out what are the key features of the surface that change the mechanical, thermal, or electrical properties of the nanomaterial, and then implement those machine learning approach to optimize the design of a nano device. So we can have a predictive system as well as a characteristic system. We were able to recognize the difference between a term called surface stress and a term called surface elasticity, because the machine learning can easily distinguish the different behavior in a wide range of tests that we can do. So these are the first pillar of what I'm doing at the moment to explore and better understand the properties of nanomaterials. The second area, or the second pillar, is how we can now when we understand the properties at nanoscale, how we can implement it for an engineering application. One of the engineering applications here at York we are focusing is on to develop new generation biosensors. One of the examples is the lateral flow test that I think most of us are familiar with that, and during the COVID pandemic. And these devices, they were trying to detect a coronavirus. The virus size is super small, it's in a few nanometers. Therefore, to detect those nanoscale biomolecules, you need to have a nanoscale device. Nanoparticles at the moment are the technology to be used for those lateral flow test technologies. And they're able to capture virus. But the key challenge is that you won't be able to distinguish between the well-attached virus or those viruses that they're not well attached or well oriented in during the detection. That could cause the problem on the false positive or false negative. It means that you might have COVID, but the device is not able to detect it or detect or diagnose the COVID, or the other way around. The device is saying that you have COVID, but unfortunately you don't have COVID because of the ill treatment or the diagnosis. And the main reason is that you need to have a reliable design to be able to predict well-oriented nanoparticles binding to the virus or those ones who are not well-oriented to bind to the virus. We were able to develop a new algorithm to include all the information from sample preparation, then implemented a conceptual design and numerical simulation for the design enhancement. So therefore, we were able to extend this numerical algorithm and implement it. And with recent finding, we were able to recognize a well-oriented nanoparticles binding to the virus with ill-oriented nanoparticles binding to the virus. So we were able to distinguish between the well-oriented and non-ones. So we were able to try to recognize the difference between false positive and false negative in the detection. And that would help us to have a better design for more reliable biosensors. Hopefully that would help us to have a better detection for an early diagnosis. Now let's try to wrap things up about what's happening in the future of the nanoscale devices and how nano device or nanomaterials are going to contribute in the future technologies. There are three areas that nano devices would be very helpful for the future technology. The first is advanced quantum devices. Unfortunately, the computing machinery is getting limited because of the heat generation and because of the energy consumption. They're getting limited. So quantum computing is getting more and more popular, and developing nanoscale quantum parts could be very helpful for scalable quantum computing. Also, because we can have superconducting features in nanomaterials, we can enhance the quantum efficiency. So rather than using a high power energy system for simple computing, we can have a very energy efficient system. Also, by the progression in AI and machine learning, we are generating quite a lot of data, and processing those data would be very difficult. So we need to have quantum computing, and hopefully nanoscale devices would be a promising application for for quantum computing. Next generation of biosensors are also an area that nanomaterials and nanostructures could help, because when we reduce the size, we increase the sensitivity of the sensor. So hopefully nano devices are going to promise ultra-sensitive nanosensors for early detection and early diagnosis. Also, as I said, when we go to the nanoscale, some materials become bendable and foldable. Therefore, we can have wearable devices. Therefore, we can have wearable devices that is attached to the skin, and we can have real-time monitoring capability by using nanomaterials. Last but not the least, we have energy crisis. We always talk about, everywhere are talking about how we can move on from fossil fuel to renewable energy and how important it is to become emission-free. And nanomaterials could be very helpful by introducing new generation, high efficient solar cells or increasing the energy storage capacity for longer battery life, and we can have a more reliable energy storage. Or another example is using nanocomposite to create next generation of wind turbines, and many other examples that nanomaterials and nanostructures could contribute into the future technologies. Thanks for listening, and that's the end of my presentation.
Thank you very much, Mohammed, for such an interesting talk related nanoscale devices and how important is the role of these nanoscale devices in the future of the technology. So now let's see if we have any question. So perhaps you can answer those questions, but at this moment, I can't see any question related to the talk. So we're going to wait a few minutes if anyone wants to ask. So we have one question right now. It's regarding nanotechnology in nuclear energy. So it's asking you, Mohammed, if you think that nanotechnology could be used in nuclear energy, helping with nuclear waste to make nuclear energy more reliable and desirable source of energy. What do you think?
Well, that's very interesting and very special question. When we are talking about the nuclear energy, we are talking about many different angles. For example, when we are talking about nuclear energy, we need to consider different phenomena or different physics that happen. In nuclear energy is not my area, but we know that in nuclear systems, we need to have proper heat transfer, as well as controlling the radiation, different radiation that can happen. And so we need to have a proper heating system to be able to do the thermal management. So therefore, nanoscale device definitely could be used for not only I'm just going to break this question down into two aspects. We could consider a contribution of nanomaterials into the technology, as well as creating a device, because when we are talking about the device, nanomaterials is doing a job for us, is doing a purpose for us. But nanomaterials could give us a unique features. For example, when I was talking about the heat transfer in battery or energy storage, we are talking about the contribution of nanomaterials to take heat. So they act as a unique features. But when we are talking about a device like a sensor, they are there for detecting, to doing the job. For getting back to the question, I think for the nuclear power generation, in both angles of creating the device for detection or highly sensitive device, definitely they could be used, as well as providing unique features such like thermal conductivity or thermal barrier, or if we need to have an insulation for radiation, definitely nanomaterials could contribute. Hopefully that I answered the question. It was a bit broad answer, I believe.
I think you did, for sure. Thank you very much. And we have a couple of more questions. Another question is about if you think nanotechnology can be used in mechanical engineering practices.
That's indeed a very interesting one, because my background is mechanical engineering, and that's the research I'm doing. If I want to give you a quick example, in our cell phone, we have something called accelerometer, which is capable to measure our step. In a vehicle, we have the same technology to measure the acceleration of a vehicle. And those sensors are based on the mechanical components, and or in a simple phrase, it's called electromechanical. So it would transfer a mechanical motion into electronic signal. And definitely those new generation of nanoelectromechanical systems are going to be used in those accelerometers, as well as biosensors, because in biosensors, when we are talking about detection of a virus, we are talking about a resonator, and that's a mechanical component. So indeed, we can have a contribution of nano devices as mechanical components.
Thank you very much. And we have very interesting question. What do you think if nanotechnology be potentially dangerous, and how?
Could you repeat the question? Sorry.
Nanotechnology be potentially dangerous?
Well, it's interesting.
It's very broad, isn't it?
I mean, indeed, I mean, every technology could bring its own danger, but at the moment, I can't think of any danger for the nanotechnology. But indeed, when we create those nanoparticles, for example, or nano devices, technically they have their own danger. because if we put nanoparticles in our skin, they could be absorbed, and some of those materials are toxic. For example, we are not able to use specific materials for biosensors because they are toxic and they could be detrimental to cells and virus or any other components. But from the other side, this toxicity helps us to do the cancer cure and cancer treatment, because those nanoparticles go and attach to the cancer cell to destroy them. So I would say it's a trade, and obviously every technology has its own benefit and its own danger.
It is indeed, thank you. And there is another question. How you think nanotechnology can be used in construction and building the buildings?
Yeah. So one of the materials which is categorized, because, sorry, I don't want to give a lecture, but we can break down materials into metals, polymers, and ceramics. But it's been a couple of decades that the new category of composites has been put in there among these three categories, and it's called composites, which is a mix of all those metals, ceramics, and polymers. And nanocomposites are a new generation of obviously nanotechnology. And composites are, getting back to the question, composites are massively used in buildings because we would like to have a lightweight buildings to be able to construct it very fast, as well as we would like to have insulation because we would like to keep the house acoustically and thermally insulated. And nanomaterials are promising for that purpose. That's one of the area for construction. Another area which I'm slightly aware of is the robots that they're doing the construction. And those robots, they need to have high resolution sensors. And we need to have a good, like a magnetoresistive sensor to be able to navigate the motion of the robot for the construction. And that would be another purpose to use a nano device or nanotechnology in construction.
Thank you, Mohammed. And I think we have another question regarding how close are you to reaching the size limit for a nanoscale device? I think they are asking from your research point of view.
Okay, yeah. I mean, when you're talking about fabricating a nano device, you could go up to 10 nanometer based on the current technology I'm doing in my research. We reach to 10 to 20 nanometer easily. If you want to make it a larger scale manufacturing, obviously you need to control the manufacturing process or fabrication process. But nowadays, researcher easily could get up to the 10 nanometer dimensions. But it depends what application you want to use, what you want to use with the nanomaterials you build. Because as I said, manipulating those nanomaterials are very challenging, and you need to have a very high resolution device for fabricating and applying those nanomaterials for different applications. So fabricating 10 nanometers is not that challenging.
Thank you very much. And the final question is about earlier, to answer one of the questions you mentioned, nanotechnology can be toxic. Is it worrying when we considering how they are disposed? Could they increase in use of nanotechnology diverse effect to sea life?
When we are talking about developing technologies in device and materials, we always need to look into the far end of the use of those devices. For example, when it reaches to the end of the life of an electronic device like a cell phone or a laptop, what's going to happen with it? We need to recycle it, obviously. Some of the structures, some of the machines are not that difficult to recycle, but some of them are quite challenging. And unfortunately, nanotechnology is one of them, especially if you have a toxic material. However, it's an enclosure protective environment, but when you want to recycle it, that could be detrimental because you have loads of, for example, nanoparticle enclosed into your device. And when you want to recycle it, it's very difficult, and you need to have a very good technology to be able to recycle them. So the answer would be yes, it could be dangerous when they reach to the end of their life, when you want to recycle them.
Thank you very much, Mohammed. That was the last question. Again, thank you very much. We found very interesting and exciting your talk. So all remains is, again, thank you very much, Mohammed. And thank you to all of you to join us. And also, I wish you a very good night.